Oh, and just there's a little bit of construction going on, like right by me. So if hopefully it doesn't get too loud. I think I moved into another room earlier today because it was getting a little loud, but I think it's kind of died down now. So, okay, so today we're going to go over section 29, which is basically an introduction to logistic regression, which really is a sneaky way for us to lead from linear regression into classification, which I think it's pretty cool. Classification is basically going to be something we're going to see a lot of with supervised learning. So we'll see this a lot within module 5, is right now on module 4. So let me go ahead and start sharing the screen. Let's see. Just real quick while I'm kind of getting this set up, just give me a thumbs up if you've looked at section 29, just so I get a feel for it. Of course, right when I asked you guys to show, you guys all disappeared. Okay, I saw a quick thumbs down from someone. Okay, so overall, I think most people haven't gone through this section yet, which is perfectly fine. Just kind of helps me out a little bit. Okay, so yes, so kind of an introduction. Note that if you have done a, if you fork this repo, so again, all this material should be on that repo that I have, like all the materials on there. I try to keep it all together. I try to organize the best I can. You can see it kind of by topic. If you have forked this recently, know that your version will probably be outdated. So just kind of be aware of that. You can do a git pull or basically free fork it or download it or whatever you're doing. Keep track of it. But we'll actually start in statistical modeling, and we're actually going to talk about it as classification. So just know there's a little bit of reordering if you have an old version of this repo. And this will lead us into the rest of the parts. Okay, so just want to let you guys know how to find that. All right, so basically we're going to introduce our first classification algorithm with logistic regression. And basically this logistic regression comes from linear regression, which is kind of cool that it actually works out this way. So the first thing to know is, what is this classification deal? Like, how is it being used? So before in the past, with linear regression, we were using basically something to find a relationship. And linear regression, I should also say polynomial regression or other things. I think if you were there for Raphael's, or if you looked at section 28, I believe, talk about extending linear regression to polynomial regression and interactions. Kind of the same idea is that we're trying to find a relationship. So like as these things change, there's some target value that changes as well. So you're kind of building more of a relationship between those two. Classification is a little bit different. So classification in this case is basically more yes, like a yes or no answer. Essentially it's like, is it this or is it not this? Now people quickly say it's like, well, like this can't be just be yes or no, because we also talk about multiple classifications. It's like group A, group B, group C. You can think of group A or group B and C as being not group A. So essentially it becomes a yes or no answer, but for each group. So it's like, is it in group A? Is it not in group A? Is it in group B or is it not in group B? That's essentially how you can do multiple groups. So the way I kind of like phrase is like you're either with us or against us, right? That's kind of like what the classification is really doing. So you can't be like an in-between classification. It's like, oh, you're either this or that. Okay, so very different from relationship. In fact, this seems very similar probably to one aspect of linear regression. Does anyone have an idea like what I'm thinking about when I say it's very similar to an aspect of linear regression? I'll start with this.
When you I just forgot the one with the one
hot meter coding.
The categorical, and you do
that's right.
Can't remember the.
Okay, no, category, yeah. That's right. That's exactly what I'm thinking, right? You would have a yes or no essentially. Like if you guys remember back when you did like the linear regression model of the waterfront, right? That was kind of like a yes or no. So instead of having it as a feature, essentially we're using that as a target of either a yes or no answer. So now that's going to look a little different. It's going to look kind of funky if we try to apply a linear regression onto this. So just to kind of clarify, is that imagine, and new color. Ooh, Zoom must have updated it. Okay, sorry, got a little surprised. I haven't shown it with Zoom yet. So if you imagine like back when we had like a two-dimensional linear regression, right? And I think the curriculum kind of shows this a little bit, is that normally we'd have like a whole bunch of, just kind of, there we go. So we have our data points. Wow, okay, well, Zoom, you stink. Okay. I think Zoom updated. Now I can't make little dots as easily. That's sad. Okay. Or am I doing it wrong? Whatever. All right. So I have these little data points, right? And then we would draw, you know, like our linear regression line. So if I have another color here and I just go ahead and draw it right through, you say, okay, like that would be like our linear regression line. However, if we had something instead where we have our data points, or let's say our axis, but our data points are either on this. Remember, this is our target, right? If I instead basically say, oh, it's either group A or group B, so we can kind of put that into yes or no answer. Well, it wouldn't make much sense to actually draw like a linear regression line through those points. Like you could technically find this and it would be the line of best fit, but it wouldn't really make sense when you look at that. It makes it seem like you can get these other groups in between here. And so that's essentially what we do with classification. And essentially, some people said like, well, we have linear regression. We understand linear regression really well. We can do all these really cool things. What if we modify linear regression to make it more something else? So this is one of my approach. It's not the literal approach of like how logistic regression came about, but essentially we took linear regression, which remember it's just a formula here. It's a little off-centered. Okay, there we go. You can see y hat is our predictive value, right? And then this beta 0, note that I kind of wrote it a little different from a normal, maybe you've seen it before, but essentially it's some constant beta 0, right? Plus beta 1 times x1, remember x1 and x2 are all features, times another number, remember those can be negative as well, all the way to n, so there's n number of features. Or if you wrote this out in notation, you would probably see something like this, okay? So remember that's kind of like how we would write out our formula for linear regression, right? And of course, this is a simple linear regression. There's no interacting features. There's no, well, in some ways you can say interacting feature like xn could be a combination of x1, x2. That could be the feature is that xn. But essentially there's different features with different values, okay? So logistic regression basically builds it up in a sense, and this is the way I like to compare it, is that we essentially are using probability to find a particular group. So we're actually defining, saying, what is the likelihood of, or say, what is, I should really say the probability, but like, what is the likelihood of being in this group A or B? And basically we can use a probability curve or a logistic curve. And so you can see here, basically we have 1 all over 1 plus E. E's, if you guys remember, Euler's number, to the power of negative that predictor, right? And if we were to kind of split this out, you can imagine, oh, it's E to basically all these different parts being added up together, those different features. And if you wrote this out even further, you might have something like this, right? Now, we don't literally think of logistic regression like in these kind of terms, but to kind of see like how we were able to get this part. Because now what happens is that we'll always have a probability if E is equal to, so usually it's negative right here. So essentially, if you have, remember how we can basically create any classification as a yes or no answer. What's the classic computer science, sciencey way of saying yes or no?
0 and 1.
0 and 1, right? Yeah. So we can basically say 0, 1 fits the predictor. Say, is it 0 or is it 1? And essentially, we can use that part to actually put in to make sure that we're always within a certain range. Essentially, we know that we're always going to be within this range. So what this looks like, and note that I kind of cheated a little bit. I took out some of the constants and stuff. So this is literally what logistic regression looks like, but it's close enough to the concept. Is that essentially what happens is that when we draw this out, if I draw out my line right here, essentially our line of best fit kind of turns into this line. Well, it's not really a line anymore. Is this curve called a logistic curve. Okay. And essentially what this is that it mostly basically, and I know that I kind of raised it up, this should actually be at 0, but if I put it at 0, it'd be hard to see. So just pretend that's at 0. But you can see here, it's basically, this is our group 1, or say no, and this is our group, our other group saying yes, right? So if you imagine either group A or not in group A, so that's essentially what this one is 0. And so we basically scale it down and say, okay, well, if you're really close off to that side right here, the probability of you being on this side, and this is our feature down here, is going to be close to 100%. So a classic example of this is saying, let's say this is heart disease. So let's say this is like a healthy heart, number 1, and this is like a bad heart, like, you have heart disease. Okay. So you could flip this around either way, but the point is that this is heart disease. There's just no heart disease, there's just heart disease on the bottom here, okay? And let's pretend that this is, well, maybe I should flip it around. I'm going to flip it around. This is going to make more sense for me, probably. Okay, so let's say this is going to be heart disease, and the bottom one's going to be no heart disease. Okay, so a healthy heart. So let's pretend this right here is going to be the weight. Okay, so if we have data points, and I'm going to go draw this in a little bit like orange. Let's try again. Okay, so you might have actual data points, like well, you're either going to have heart disease or not, but you're going to have certain weight. So we take a whole bunch of people, and we find that a lot of people who are on the lower weight, don't have heart disease. But there's some people who are on, still high weights who don't have heart disease. So we can see here, as we increase weight here, there seems to be more people who are on the lower end here that don't have heart disease. And then as we get up here, maybe you see the data points kind of look something like this. Maybe there's some people who are really light but still have heart disease, and then people who are heavier that have heart disease. Okay. And so the idea here is that what this curve is describing is saying the likelihood or the probability that given a weight, you have heart disease or not. So because this will always go from 0 to 1, we can actually scale it down to make sure there's always 0 to 1. You will always have a probability of % of saying how likely are you to actually weigh this. So if I have, for example, if this represents weight 100 kilograms, right? So well, 100 kilograms, and you go right here, it's like, well, okay, that means that at 100 kilograms, you are like, let's say, 85%, likely to have heart disease. Versus like right here, you might say, okay, like if you are, let's say like 85 kilograms, there's a 50% chance that you'd say you have heart disease. If you are like, let's say 75 kilograms, you might say, oh, you only have like 15% chance of actually having heart disease based on the data. So essentially this logistic curve can help us predict basically on how well. Oh, I see what happened now. My chart is not plugged in. But you can use this logistic curve to figure out the probability of like, what this is based on the data. So this is a lot more meaningful than compared to just drawing a straight line through. You're trying to basically say some kind of relationship where we just want yes or no. Okay. Any questions on how this logistic curve can help basically be used for classification, how it relates to linear regression in this way? Thumbs up, thumbs down, I think I'm pretty good. Okay. I see some sideways. So those people kind of like, giving a little hot nods sideways. Are there any questions that you have in particular that kind of would help make this clear?
I don't have a question, but I don't know if it's just me, but I'm having a little bit of a hard time hearing you. It kind of sounds like you're speaking in a tunnel. I don't know if it's just my computer.
No, I bet it's me.
Yeah, me too, actually. Yeah.
Oh, yeah. I see why.
Is this better? Okay, cool. I have an external mic and it was using my computer's mic, which is way over there. So that kind of makes sense. For the record, if that ever happens, let me know. All right, let me plug in my computer because I can see why it's not charging now. All right. Sorry, everyone. Craziness today. Okay, so you can hear me. My computer actually has power going to it, so I won't finish the lecture in the middle of like of talking or something. Okay, cool. So I'll move on then to actually implementing this. So, all right. So if you're following along like on like the repo, note that you just have to click on this notebook. Basically on this link, it'll take you to the other notebook. So if I click on here, cool. So now let's go ahead and try implementing logistic regression. So note basically that there's a couple ways you can do this. I think the curriculum shows first with stats models. As you guys probably know by now, is that I'm not a huge stats models person. I definitely like using sklearn a little bit better. Note that there are some disadvantages of using some of these older, like not older, that's not the right way to say it. Basically, these well used methods like linear regression, ANOVA, and things like logistic regression. So like one thing that the curriculum talks about is that you won't get like a readout, like a nice table of telling you about all the information. For sklearn, you kind of have to pull it out directly. But for the most part, I'm going to use sklearn because that's, to be quite honest, a little more common. So, all right, so we're going to go ahead and note that these are typical imports that we normally get. I'm going to import data sets from sklearn. So sklearn actually has data sets already built into it, which is super nice. And then this is the stuff that we're actually going to use to actually model. So note that I'm going to do some pre-processing just to kind of show you what that looks like. It's not necessary, but it's helpful. Linear model, so basically from sklearn.linear model, okay, from this package, we're going to import logistic regression. And then we'll also get train test split. So remember, we want to be careful. If you remember from section 28, you have to make sure that you want to make sure you don't have too much bias and everything like that and overfit. So this will help us gauge that and make sure we don't overfit and all these things. Okay, so we go ahead and import those parts. And now we can go ahead and start playing with this data. So I'm pulling this iris data, which is a relatively small data set. Basically, I think it refers to like different flowers, stuff like this. So if you look at the actual information, you can see there's sepal length. I don't even know if that I'm pronouncing that right, sepal. And then note that we also have petal width and the target. Note that the target is actually going to be different classes. And this is why I'm using this data set, is that essentially, this is like different kinds of flowers, essentially. So you can see here is only 150 data points. So it's gonna be relatively small, but it helps us be able to visualize everything. So you can see here the different targets, which are all this guy right here. It just goes 0, 1, or 2. So you can kind of get a feel for, you know, what this data set kind of looks like. And then of course we have these different features, 1, 2, 3, 4 different features, okay? So just to kind of show you like what this would look like if you were, before you did linear regression, I'm gonna basically make some 2D plots, each going through. So this is something, again, like as you kind of play around with, you know, plotting, you might find things. This is basically making different subplots. So in here, I'm just gonna walk you guys through this part because it's something I haven't shown you guys directly, but maybe you come across it yourself or you saw in the curriculum, is I'm making the figure itself. So I'm making a certain size of the figure. And then basically this guy right here is going to iterate over 0 to 4, basically to count, basically keep track of which plot I'm doing. I know I'm going to do 4 because I have 4 different features. So I want to have one that's target and then the feature over here. Actually, I think I might have that switch over. I actually have the target on the x-axis, and on the y-axis is actually going to be the feature, which is usually backwards, but it's a little bit easier for us to see. So I'm going to go ahead and do this part, and you'll see basically I have a little bit of extra information. I also put alpha as 0.01 or 0.1, just so we can see a little bit better, so there's clustering. So you can see here, note that 0, 1, and 2 represent the actual targets. Basically, it's flower 0, flower 1, flower 2, those different kind of species or whatever we're looking at. And then each of these parts are actual features. So you can see here is that it wouldn't make sense for a lot of these things to actually have linear regression because we have a lot of variance on the different parts. So, but you can imagine maybe as a combining these together, maybe we're saying, okay, well, if your sepal length is very small, but you have, I don't know, a medium-sized petal length, then that might be something that's like, oh, these are important parts. That means it should be class 1. Or something similar where you have petal length and petal width are very similar size. Maybe those things mean that they're likely to be class 1. So you can kind of see an idea of like how you would use these together to figure out which one's which. Okay. So any questions on what this data represents and what we're looking at? Cool. Sound good? All right. So this is just a quick exploration of the data. So we haven't actually done anything yet. So now it's actually preparing the data so we can do classification. So I'm just going to make these smaller so we can focus on these parts. Okay, so the first part is getting our X. Remember, X is our actual target. I'm using iLock here, basically because I have this nice data frame that's all the way up here. Here it is. I just want these guys without the target, right? So I'm going to get everything, where am I? Oh, everything except for the target, right? So remember, this represents rows. This is going to represent columns, everything up to the very last column. So we're going to ignore column. I could have done the same thing with here, but since I already have the target already defined within the data frame, I can just basically use that. So I'll have X and Y. Note that I'll also normalize X. This is not necessary for this case, especially for such a small data set. But a lot of machine learning algorithms will likely need to be normalized or scaled in some fashion. So this is pretty standard practice. Logistic regression, you can probably get away with not having to do this. But for other machine learning algorithms, it's definitely necessary. So we're just going to go ahead and do it just to keep it consistent for future stuff. And then note that this is, I think I mentioned this like if you remember, way before back in like module 1-ish, right? I talked about test train splits. And this is how you would do a test train split for machine learning, is essentially you'd want to split it up before you actually fit the data. So note that I'm not actually fitting the data here. And this is so we can actually compare and evaluate our model and say, hey, like, does our model actually work? Note that if you didn't do a test train split and you basically just went ahead and ran the whole model, well, in order to evaluate it, you would have to get new data, right, to test it out and see did it actually work well. Why couldn't we just use the same data like after we trained it?
Because the model might be overfit then? Is that?
Might overfit it. It's even more, it's in a lot of ways worse than that. Put it another way is if I were a teacher and I were giving like a class of like 6th graders a test, right? And I gave them the test to go study from, would I just give them the same exact paper to test them? Yeah, I see some head shakes. No. And why is that essentially?
Because they would just like learn the test, not necessarily like the concepts.
Right. We want the students to learn the concepts, right? We don't want them just to memorize the answers to the test. Essentially, essentially what machine learning does, it's trying to learn from the material, which more or less is basically it memorizing the answers. But the problem is if we only evaluate it by using what it learned off of, we can't actually reliably know if it really did, like, you know, I put in quotes and learn, but like basically learn the information, like the idea of it versus just memorizing a bunch of answers. So this is why we do a test train split before we do the training. Okay. So I now have my train information, my Y-train. So note that this test train split is built into sklearn. Note that I also put 20%. So basically 80% of the data is going to be used to train, 20% should be used to actually test it out. And then I put a random state 27. This is just basically so I can be consistent every single time. Note that's just a seed. This number doesn't really matter. It's even optional. But if you want to make sure your model works properly, if you try to run it again without a random state, you won't know if it's just randomly like works or if it's because of that random state. So this is usually good practice to put in. And you can put whatever favorite number you want. You'll see a lot of 42s, for example. Okay, so now we can actually create the logistic regression model. So,
sorry.
oh yeah. Yeah,
in this case, you should also normalize after doing the train test, or
yeah, this is actually, you know, to be quite honest, good catch, Marto. This really should be done after our test train split. It depends. Well, okay, I won't say that. You might have something called data leakages, and you have to be really careful about that kind of stuff. So by normalizing it beforehand, it might remember some information from the train that's put in the test. So note that it's basically seeing, in some ways, some aspect of the test results before it's ever seen it. So just kind of be aware of this. In this case, just an example, I'm being a little, to be honest, I'm being a little fast and loose with that concept. But good catch, though, I think, Bardo, if that's what you were trying to get at, doing the normalization before or after the test train split. Yeah, cool. And generally is that if you already know what like the values are going to be ranging from, normalization usually is fine in that case, making sure you know it's going to be in this range anyway. So this is the most and maximum. For example, I'll just make something up, right? It's like if you're talking about percentages, you know it's always going to be 0 to 100. Well, let's pretend this is 100% capped off. You know that's only going to be a certain value. So normalization should be fine in that case. Good subtle catch. Cool. All right, so assuming we have all our data test train split properly, it's all set. Now we're actually going to use that training data to basically fit on the logistic regression. So note that this is logistic regression. I could have, I think by default, I could have just done logistic regression like this. I'm putting some extra parameters in there to make sure it works properly. These are things that you can look at, for example, in the actual details of how this works. We're just going to quickly go through. Basically, it's saying, do you care about the intercepts? Like, no, we're going to ignore this intercept right now. This solver basically is an optimizer. I probably could have left that out because it's a relatively small data set. Basically, it's like saying, how do you solve the logistic regression thing? There's different ways you can use the solver. This is all built into sklearn, different options. So this matters a lot if you have very large data set where you might care about what solver to use. And then multi-class, note I put auto, basically saying that there's multiple classes in here. So go ahead and treat it, you know, figure out what the classes are. So I don't have to tell it's like 0, 1, and 2. Okay. So once I create this part, and I'll show you what this looks like so that way you guys can see. So I basically create my logistic regression. I have not fit it. Basically, it's like a model ready to go. It's ready to be trained. And now I basically feed it in its trained data as well as the predicted, the actual trait, the actual classifications. So if it's 0, 1, or 2, this is how it's going to learn essentially. So I do this part right here. I run this, and you can actually see I have a model now. This model log, right? It's basically a logistic regression. It has a certain C. It has some extra parameters and stuff like this. And we can actually see how well it goes. So this is actually all set and ready. But we want to see how well did it do, right? So we can see here, let's see here. Okay, so I'm getting some information on this part. So I can basically make predictions off of the test set, which it hasn't seen. I can also make predictions off the train set, which it has seen. So it should do pretty well on the train set. Or let me ask you guys, would you expect these to be the same, or do you expect one to be better than the other between it predicting on the test set or predicting on the train set?
I mean, it's probably better on what it trained with, right?
That's right, right? So you would expect it to do pretty well on this. So that's why we still have to test it, do on the test set to make sure it actually worked, right? Or at least evaluate how well it worked. Okay, so I just want to check your guys' knowledge on that. All right, so you have test and train. Now we can actually evaluate this model. So first thing I'm going to do is just look at our training set, since we know it should do decently on this, right? So note that our residuals are just going to be saying when is Y train, which is basically its prediction. I'm sorry, it's Y train is the actual label if it's 0, 1, or 2, and Y hat train. Y hat train is basically what we predicted off our model. So our model, we fed in the features and said, okay, what should for each of these features, what should be the predicted value? And say, okay, is it 0, 1, or 2? So our residuals are basically just going to say, are they equal to each other? Is it a 0 when it's a 0? Is it wrong? So basically we'll get a true, false, true, false. Note that this will actually be, let's see if I can run this right here. If I run this right here and I do residuals, what do you guys expect this to look like, this residuals? Like if I press enter, what will get printed out?
Trues or falses?
Yeah, true or falses, yeah. And just to kind of show you guys, thank you, Hazel. Just to kind of show you guys what this looks like, if I do Y hat train, that's just going to basically 2s, 0s, and 1s, saying which class it is. And then Y train itself is also going to be the same number of trues and falses, right? So you can see here. Okay, so then it's just a series that all I'm going to do to compare them. So if I do, I'm sorry, not true and falses, 2s, 0s, and 1s. So now if I compare the two, basically say, are those equal? We'll get, like Hazel said, a bunch of true or falses. So you can see here, most of these are true. It looks like we got a false here. So what's nice about this, though, is that we can actually, first of all, the reason why we care about true and falses, these are actually treated as 0s and 1s in Python. So we can actually treat these as 1s and these are 0s. So it makes it a little math a little bit easier. So we can do, for example, if I did sum, what should that, if I do sum like this, what should this represent?
All the counts of true.
Right, so count how many truths there are. And if I did, let's see here, I'm trying to think of a good one to do. Okay, we'll just, we'll do 1 minus residuals. What should that give? It's a little trickier. What's 1 minus residuals give? So you can see here is that essentially did 1 minus true, right? Or 1 minus false. Well, true is 1, false is 0. So 1 minus true, 1 minus 1 is 0. So basically this broadcast out. Remember, this is like a NumPy array. So essentially this will act like a huge big array of saying 1 minus then whatever the number is, which is either true or false, or 1, 0, and 1. So note that these were all true before, and then our 1 false is just 1. So if I did sum of 1 minus residuals, what should that represent?
The ones that are false.
That's right.
Some that.
Yeah, that's right. So residuals, like Ali said, sum of residuals is just going to be the number of true. Sum of 1 minus residuals is just going to show us how many are false, right? So we see there are 3 false ones, and I think 117 were true. So if I run this right here, you can actually see 117 is true, 3 are false. Okay. So no, I was just showing you a little different way that you might see every once in a while going through and what that looks like. But the concepts are the same. So you can see here, we're pretty good on our training data, which we would hope, right? We got a little bit over, that's what, like at least 99%, right? 98%? Yeah, it's about 90, it's about 98%ish, right? A little higher than that. So anyway, or no, sorry, I'm doing math in my head. It should be a little bit about 97, 98%, somewhere between that two. Okay, so pretty decent, right? Which we would hope for, right? And we can also—
Is there like a rule of thumb for what it's supposed to be, or what is like good?
But what is good?
Yeah.
Good would be 100%, right? So we would predict everything. But of course, yeah, this all depends on context of like how well can you actually predict, you know, maybe these features, for example, if these features were just like, was it sunny that day, when the flower was looked at, like that probably wouldn't give anything. So that would probably be like 50%, or, you know, random chance, like 1/3 of each time, right? So this is where, to be honest, it depends on the situation, on what's already done. Sometimes research is useful to see what has already been done. You know, like, has someone gotten, you know, this level of percent? Like, is the best thing that someone's done 80% and you got a 98%? Like, awesome, right? Maybe the best has only been like, you know, 70% and you get like an 80%. Like, that's a significant result. Like, that's a good thing. Opposite might happen. Like, was like, oh wow, I got 95%, but like it's pretty typical to get like 98% accuracy on this part. And this is where actually evaluation metrics will come in handy. Say, well, okay, how do we measure what is good, you know, and compare those parts? So a good question, because it's not directly obvious, because it all depends on context. So cool. All right. And then, like I said, percentage, I forgot, I actually did this part. We can actually get the percentage. So you can see 97.5 and about 2.5%. So 2.5% of the times we didn't quite get it right. But everything else, almost 98% of the time we got it correct. So cool, that's great for training. But now we got to see, okay, what about data it's never seen before? And that's where our testing set is from, right? So note that I'm doing the same residuals, but in this case, I'm using the test set, right? So remember that we already made this prediction from up here, right? So we predicted off this test. So we used the regression model that we trained with the training data. And now we have new data that it's never seen before. And we're putting that into the linear regression and seeing how well it performs. So we can see here is that if we do the residuals, okay, so remember this would be just a bunch of true and falses. We can actually see how many true and how many false. So you remember we only did about, was it, I think 20%. So only 30 of the 150 points. So out of the 150, or out of the 30 points that it had on the test set, 28 were correct and 2 were false. So you can see it percentage-wise, it's about 93% correct and like about, was it 6% incorrect. So not too bad, but you can definitely see that it didn't do as well as this training set. Okay, and it turns out from the solver, this is probably the most optimal from the features that we have itself, especially considering it's so small. It's pretty easy to figure out which is the right, what's it called? The right logistic curve to predict these parts. Okay, so that is logistic regression. And from there, you can say, okay, cool, we predicted it, we did well, that's the percentage, right? Any questions on how we perform this, or anything else that we might even talk about? Thumbs up, that sounds pretty good. Thumbs down, you're like, I don't know what happened. Sideways, you're like, I think I get it. I see most of the thumbs up. Good, that's awesome. And you think of this, most of this is pretty simple, right? Most of it was just creating, separating the data out, creating my logistic regression, possibly with some extra parameters, and then just training it. And then we just tested it out with the residuals of saying, how well did it perform? Now, this is where it comes fun. It's like, you know, Tara, if you asked this like, you know, 2 minutes later would be perfect. Perfect segue, because Tara's question would have been, but what's a good model? You're like, oh, that's a great question, Tara, because that leads us into evaluation. So we actually want to see, hey, evaluating from this model, how well did we do?